he's Patrick. He's a particle, but he's kind of boring because all he does is move in a straight line back and forth with respect to some fixed point. I want to have a look at how he's moving, but in relation to this fixed point. The distance away from the fixed point we call displacement, and there's a subtle difference between displacement and difference. However, displacement is the distance measured with respect to a fixed point, where the direction will determine if we have a positive or negative displacement value. Take Patrick's movement for example. We can measure the displacement by considering positive displacement values when Patrick is to the right of the fixed point, and negative displacement values when he's to the left of the point. Here, see how it plays out again. And in addition to displacement, we can also have a look at Patrick's speed. If we watch, there are moments where he seems to be moving faster and moments where he almost stops. You could say that his speed would describe how his displacement is changing, and you'd be correct. The rate at which displacement is changing is called velocity, a kind of directional way of measuring speed. If we consider Patrick moving back and forth from this fixed point, we can analyze a velocity graph, where if he's moving back towards the fixed point, or in other words, the displacement is decreasing, then we would say he's got negative velocity. And in fact, the velocity describes exactly how the displacement is changing. And to really summarize, the rate of change of displacement is velocity. We can see this play in sync with Patrick moving along his line, and watch how the displacement and velocity are related to one another. This is just an intuition of an example I grabbed from a textbook, and really all it's telling us is that the derivative of displacement with respect to time is velocity. And so I've just grabbed it out here. It's a particle's moving in a straight line, d meters relative to a fixed point O, on the line, and it's given by some trigonometric equation because his movement is wave-like, where t is the time in seconds, and we're just going to measure between 0 and 24. Now the first part of this question is asking us to sketch the displacement function, so I'm just going to sketch this function here. And so there we can just see this is sketching a trigonometric function, stuff we've done in Unit 2. Right, so that would be the first part of the question. And you should notice that that is actually the displacement function from the animation that we saw earlier. Right? Now the next part of this question is asked me to determine what the velocity and the acceleration functions are. We're not being asked to sketch them, but we can determine what they are because I know that the velocity describes how the displacement is changing. So that means that the velocity is equal to, and I'll call it v of t, is equal to the derivative of displacement. And so I can differentiate the displacement function. I know it's 2 up here, 2 cos of pi on 12t plus 1. I've got 2 times by the inside function, which is linear, so it's pi on 12 comes out, times by the derivative of cos is a negative sign, and that pi on 12 comes out there, and the plus 1 goes away because it's a constant term, and I would simplify that, and I'd say I've got negative pi on 6 sine of pi on 12 t, and that would give me my velocity function. Now, similar with velocity describing how displacement changes, acceleration describes how velocity is changing. So if I want to find the acceleration function, a of t, I would say that that is the derivative of velocity. And so that would tell me that I just have to derive this guy right down here, this velocity function. And so I've got negative pi on 6 multiplied by pi on 12, take the derivative of sine, and I'll get cos. And when I clean that up, I get negative pi squared over 72 cos of pi on 12t. So that would be my acceleration and my velocity function. Okay, where if you're looking for a little acronym, it's a displacement, derive that, you get velocity, derive that, you get acceleration. And so that is called DVA or DIVA, or I don't know, whatever you want to call it, but that's a little acronym for it. And so I've established those functions there. The next part of my question here for part C is saying, determine the maximum speed when this occurs and the position of the particle relative to O. And I know that the position, I've already seen a description for that. The position to it relative to O would be its displacement. So really all I need to find out is determine the maximum speed would occur when the derivative of the velocity is equal to 0. Because if you want to have a look at how the velocity is changing, its maximum point would be where the slope is equal to 0. Now, it turns out that the derivative of velocity is acceleration. So I can set this acceleration function equal to 0 and solve that. So I'd have, using this as my acceleration function, I set that equal to 0 and solve for t. Okay, where this is something I can definitely solve, I'm just going to divide both sides here by negative pi on 72, pi squared on 72, because that'll just cancel with that, and 0 divided by pi squared, negative pi squared on 72 is still just 0. So I'm going to have 0 equals cos of pi on 12t. And I might just finish this question up over here. This occurs when, okay, this occurs at pi on 2. That's when cos is equal to 0 at pi on 2. So the implied logic here is that this stuff has to equal pi on 2. So that is my equation that I can solve. I say I've got pi on 12t equals pi on 2. Now with a bit of rearranging here, if I multiply both sides by 12, I get pi t equals 12 pi on 2, which I can cancel off to just get 6 pi there. So I've got pi t equals 6 pi, and I divide both sides by pi. And what I'll get here is t is equal to 6. Okay, that would be one of the maximum speeds. That would be one of the maximum speeds. I also need to consider that this equation down here is going to occur when cos radians is 3 pi on 2. And so really where I'm drawing this logic out here is actually from the unit circle, where I've got my sine axis and my cos axis. And I'm saying that sine is going to be equal to 0 at this point here, and it's also going to be equal to 0 at this point here, which is pi on 2 and 3 pi on 2. And those are giving me my equations. So now I'm going to have pi on 12t equals 3 pi on 2. Equals 18. And if we actually have a look at our animation again, the velocity graph does exactly describe this, and we can see that the maximum speed is occurring when t is equal to 6 and when t is equal to 18. However, this isn't the full question. The question is also asked us to and determine the position of the particle relative to the origin. So I need to just evaluate the displacement at these points. So d of 6 is equal to and d of 18. And just to remind ourselves that the displacement function was equal to 2 cos of pi on 12t plus 1. So when I put that in there, I'm going to get 2 cos of, that's going to be 6 pi on 12 plus 1, where that will just become a half, so pi on 2. 2 cos of pi on 2 plus 1. That's just going to occur when the displacement is equal to 1, because this is equal to 0. So 2 times 0 plus 1 is 0. So I'd say So I know that d of t is equal to 1, and the implication of this is that it is 1 unit to the right of the fixed point. Because I know when I've got positive displacement, this is a positive number for displacement, I have got my particle going to the right, and that direction is important. If we do a similar thing for 18, we get this is occurring 1 unit to the right. Okay, and our last part of the question here is just saying determine the total distance traveled by the particle. Now we can actually just analyze the displacement graph here, where I know, and I can take the fact that I know that my particle is just traveling in a straight line. So if it's gone from 3 units being away to the fixed position to 1 unit away from the fixed position, in those 6 seconds it's traveled 2 meters. I can also use this implied logic here to go from, well, it's gone from 1 displacement to -1 displacement. That means it's traveled 2 meters in the left direction. So in a half of its cycle, it's traveled 4 meters, and you can pull out the same logic here again between this point and this point. It's traveled another 2 meters, and then in its last lap, it's traveled another 2 meters there. So I would say that the total distance is equal to 8 meters. Okay, that's just a little bit of interpreting there.